The next level in relativistic calculations is really adding velocities. You've got your Lorentz transformations now, and you're feeling okay with them. You know, length contracts and time dilates. But who's to say what happens if you have a really complicated situation where like 3 things are moving? This is where it gets kind of gross. I just want to remind you that this is the answer that we're going to be trying to explain today. That is how one thing sees these other 2 things moving relativistically. And here's like the picture. Okay, so this guy right here, this is a bullet that was fired by this little spaceship right here. And the guys in this spaceship see the bullet going at half of the speed of light. But at the same time, this spaceship is flying away from this monster spaceship at half the speed of light, right? And so you could ask yourself, I'm not going to be really careful with these labels because I just want to set up the problem here. You could ask yourself, if the monster looks at the bullet, how fast does the monster think the bullet is going? And of course, it's unreasonable to say c. The bullet cannot go c. And so we have to use this complicated method of combining the 2 velocities. This has a, I'll call it like a regulatory denominator that makes sure that the sum of these 2 does not add up to c ever at any time. So we're going to try to understand how this is possible because this is moving relative to this, and this is moving relative to this, and so this is moving relative to this, and all the speeds are relativistic, and so it's complicated. It's complicated. That is our relationship with, with relativity. Okay, so what you need first is a diabolical timing device. First, you have a source. Oh, that's gross. Let's make a proper source. I'm going to write the word source, and then I'll box it in. There's a source, and the source is sending particles this direction, and they're going at a speed v prime as seen by someone who is at rest relative to the source. Now, the source is not moving, according to this observer. I'm going to call the observer O prime, at rest relative to clock. This is my timing device. It's actually a clock. Over here, I have a flash, and the flash is triggered. There will be light shot out from this flash when the particle arrives, and it's an automatic kind of thing. It's just chunk, chunk, and it takes no time at all. So when this particle gets over to here, and these are probably some distance, what do you want to call it, L naught? Yeah. There's some distance L naught apart, and when they are that distance L naught apart, this is triggered right here, and a photon comes out of here. I'll draw it as a little squiggly, a wave packet going that direction. And guess how fast it's going? It's going the speed of light, of course. Everybody agrees on that. And over here, there's a detector. Okay, so you've got your source sending out particles that slam in over here and immediately trigger this flash. And the flash sends a pulse of light this direction, and that's considered 1 tick of the clock. Immediately when the detector detects the photon getting there, the source sends out another particle that goes over to the flash, etc., and it's going tick, 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 tick regularly. Now, this L naught is the proper length between the source and the flash, and it's the proper length between the detector and the flash. This is all assumed to be horizontal, and it's the proper length because that's the longest length that anyone will see. So I'm going to call this time delta T naught, which is the time between ticks measured by O prime. This is the time measured by this observer, by observer O prime, and the observer who's at rest relative to the detector, O prime, is going to find delta T naught to be the sum of 2 times. That time is going to be the time that the particle takes to get to the flash, plus the time that the photon takes to get back to the detector. And those are the same distances, so to get those times, you're going to have to take the distance and divide it by the velocity. So here's v prime, the velocity of the particle, as seen by an observer O prime, and then I'm going to add that to the time that it takes the photon to get there, which is just L naught divided by c. So here we have light time to go across that L naught, and here we have particle time. Particle time, light time. Which one's longer? Okay, you figure it out. But along comes Mary. And Mary is observer O. Mary is moving to the right. Mary is moving to the right. No, that's not good. Let's have her move to the left. All right. Actually, Mary's moving to the left because when Mary looks at observer O prime, the apparatus, she sees the apparatus moving to the right. So observer O sees, sees O prime going right. Now, of course, we can just make this variable that I'm going to say, the relative velocity between O and O prime is U. We can make U negative if we want Mary to go to the right. But as it is, as I'm going to argue this, Mary's going to the left, so she sees this entire thing going to the right. Now, that's going to make the time that she observes very different, right? She's going to see the particle moving at V. Okay, let's, well, we're not gonna have enough room to do all this right here, but we'll just get started. She sees particle at V, and it reaches flash. When does it reach the flash? Well, it's going to take a time that she'll call delta T1, and that's the time to reach the flash. But delta T1 is, well, oh gosh, we should figure out how far it's gone. How far did the particle go? Let's try to get organized here on the next page. What Mary saw. Particle at speed V goes distance V, well, let's see, it's going to be V times T delta T1. That will be the amount of time that she sees it moving, right? But V times delta T1, how far the particle has gone, this is according to Mary, right? So she's going this way, and she sees the particle having to go much farther because the flash is getting farther and farther to the right. So that's going to be a distance, L, plus U times delta T1. This is how far flash moved. And this is the contracted length. Because, of course, Mary does not agree about the separation distance. Mary doesn't think that it's L naught between the source and the detector. She thinks that it's something a little bit shorter because she's not in the, she doesn't measure the proper length because she's moving relative to the experiment. So this is how far the flash moved away, and this is the contracted length, and this is the distance that the particle has gone because she sees it going for a time delta T1, and she sees it going at a speed V. So all this kind of makes sense. This is all according to Mary. This whole page will be according to Mary. Let's do a little bit of, can we handle seafoam green? Well, we could try, I guess. Then light at sea, of course, travels. Well, we can define in the same argument that it's C times delta T2. That is the time that Mary thinks it takes for the light to get back this direction. But remember that Mary thinks the whole apparatus is moving to the right, so she thinks that the detector has actually moved towards the light, and so she thinks the light hasn't gone nearly L, which would be her contracted length. But here's what she sees. She sees it going a length L minus U times delta T2. Is that fair? So here we are with the contracted length again, and this term right here is how far the detector moved closer. Okay, that's tricky. The whole clock moved to the right, and then the detector ended up moving to the right after the flash, and so that distance got shorter. Okay, oh yeah, the light was going left and the clock was going to the right, so that shortened the distance. So I'm just going to solve these two equations for delta T1 and delta T2, and then we'll take a brief break because I have some local responsibilities. Let's see, let's solve this one for delta T1. Delta T1, I'm going to get L, and then I'm going to get, well, let's see, I'll take this over to this side. It's going to be V minus U times delta T1. So I'm going to get L divided by V minus U. That's what delta T1 is, and delta T2 is a little bit interesting. Let's see, I'll move this over to the other side. I'm gonna get, well, I gotta get L divided by, oh shoot, it's L divided by C plus u. Oh, that's really interesting. So let's put these guys in little bubbles. And let's come back to it in just a moment. You don't have to wait a bit, but I have to wait a long time. Bye-bye. Okay, fresh battery. What's really interesting about what Mary saw is that we know the time that Mary believes took place in between the source emitting a particle. Here's our picture here. The source emits a particle, the flash gets hit by the particle and sends out a photon. We know the time that Mary thinks this particle takes to get to the flash, and we know the time that Mary thinks the photon takes to get back to the detector. These are delta T1 and delta T2 respectively. If we add those together, we find delta T, which I'm going to call the time that Mary believes takes place during a tick. So this is Mary's perception of the clock's time-taking ability, and that's going to be L over V minus U quantity plus L over C plus U quantity. We're going to have to be very careful because we're going to do a lot of algebra, but I don't think I've made any mistakes yet. So that's good. And the only other thing that we should note before we continue is that, what? Oh, well, Mary is quite capable also of doing the Lorentz transformation to find out how delta T naught relates to delta T. So let's go back and think a little bit about delta T naught relating to delta T. I believe that delta T, this is going to be called dilated time because time dilation is a thing in relativity. This reminds me of the band Dilated Peoples, and maybe that's a pun on dilated pupils, but it also means that the people get larger, which is really the beginning of the revolution. So we'll say delta T equals gamma times delta T naught. And gamma is always greater than or equal to 1, so this is a longer time in between ticks that Mary thinks. Mary thinks that the detector and the flash and all that stuff, she thinks that they're telling time slowly. So that's okay, because that's her perspective, and this is proper time. And the proper time, of course, is what's measured in that rest frame relative to the whole thing. But we're going to have to define gamma carefully, because gamma is the relationship between what Mary sees in her frame O versus what is happening in the clock's frame of O prime. And so gamma here, every time I'm going to use gamma in this entire derivation, it's going to be 1 over 1 minus, well, it's all under a screw, right? But I could put V here, or V prime here, or U here, and I want you to try to figure out why I, put U there instead of all those other opportunities. So this is 1 minus beta squared. Okay, great. But you got your gamma, and you got your dilated time, and you got your proper time, and there's this other thing that I always remember. This is contracted length, and it's related to a dilated time. We've got that same kind of gamma happening there, but this is contracted length because Mary will believe that the distance covered by the particle and the photon is shorter than the distance that the people at rest relative to the clock believe actually took place. So we've got an L naught here over a gamma. This shrinks the proper length. We got the proper length right there. Again, measured by the person at rest relative to the experiment. Okay. So let us go to figuring out, well, what do you want to do now? You want to say that remember what we had? Oh gosh, like at the very beginning, we defined something called delta T naught. Let's see if I can find it. Here it is. Delta T naught was this stuff right here, the time for the particle to go and the time for the light to go as seen by the person in the frame of the detector. So I'm going to say delta T naught equals, well, actually, you know what? I'm going to start this a little bit differently. I'm going to say delta T is gamma times delta T naught, and now I'm going to plug in what delta T naught was. So I'm going to do that in, let's do it in tropical violet. This is a fine thing to do. Gamma times L naught over V prime plus gamma times L naught over C. This is just gammas times the delta T naught that we had on the previous page. Check it. Seriously, it really is. But this stuff right here is reminiscent of what's going on over here, right? Like, what if I solve this equation for L naught? I know that L naught is gamma times L. I could take that and I could plug it in right there and right there. This is interesting because then it tells us that delta T is in fact, watch this, gamma square L over V prime plus gamma square L over C. That is the amount of time that Mary perceives happening during a tick. But we also know that the amount of time that Mary perceives happening during a tick is, wait for it, I know I wrote it somewhere, this time right here, this is delta t. Now, would you believe that delta t is equal to delta t? Please say yes, please say yes, please say yes. I can't hear you. Is anybody out there? Do you think it is? Delta t. She says delta t is equal to delta t. So I'm going to take this delta t right here. Let's destroy things together. This delta t right here. And I'm going to take this other delta t, which was on this other sheet right here, just to prove to you that I'm not making this stuff. You can't make this stuff up. You think Einstein was trying to give everybody a headache? He was actually a really nice guy, but he did still give everybody a headache. These are both delta t's, and I'm going to set them equal to each other. Watch as I, what am I going to do? I'm going to slide this down here so you can see, then leave me a time back up there, because delta t is the delta t. Delta t equals delta t, and I'm going to get that is L over V minus U plus L over C plus U, and this side is gamma square L over V prime plus gamma square L over C. Now, I've got to slide this back up so that we can see. But that equation right there is relativistic velocity transformation. Typically, in a textbook, if you're reading about this, it will say, the rest is algebra, left to the reader to enjoy. But I'm your guy in the trenches, and so here we go. We're gonna do it. What I notice first is that there's L all over the place. L, 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 L. Okay, so these are just V minus U and C plus U. No! Gosh, they're 1 over that nonsense. But here's what I'm about to do. I'm going to multiply everything by some stuff. My plan is what? Where do we go from here? I'll be right back with you. Oh, of course, what's your very least favorite thing? Denominators! Let's take the entire thing and multiply it by everything so we have absolutely no denominators. That means I'm going to multiply by, literally, I'm multiplying by V prime times C times V minus U times C plus U. See, as I multiply by all of this stuff and things come out in a very bleak and messy form. Watch this, I'm going to have V minus U canceling here, but this term's going to be left as V prime C times C plus U. And this next term, the C plus U is going to cancel out, so I'm going to get left here. It's going to be V prime times C times V minus U. And this next term over on this side, well, we're not going to have a V prime, but we'll have all the other stuff, and we got a gamma squared. That's gamma squared times C times V minus U, also times C plus U. Just because we hate denominators, we're doing all this. Plus gamma squared, and then I have to multiply by this stuff. The C is going to cancel. I got a V prime. Whoa, whoa, whoa. Stop me if you see that, internet people. V prime, and then I'm going to multiply by V minus U, and then I also have to multiply by C plus U. That's going to be in parentheses as well. So that parentheses is overlapping that parentheses, but everything is still okay. We just barely fit it on one line. Now, one thing that I think is actually really cool is when we spread this out a little bit, yeah, that's right, I'm going to be distributing, and it's going to be very, very gross. But some cancellation will happen, and so it's worth our while. In teal, V prime C square is this first term as we go ploop, and then we're going to go ploop. I'm just going to be distributing a whole bunch of stuff like spreading grass seed upon a nice early spring morning, and we're going to get some, what are we going to get? I'm going to get a V prime times C times U. All of these should have 3 velocity terms multiplied together, and they're going to be really weird forms, but we'll just confirm that each of them has 3 velocity terms so we can check our work. And then we've got another V right here. Notice V and V prime are not the same thing. They're those relative velocities of the other things. And then they're going to have a minus sign right here. This is a V prime and a C and a U. Oh my goodness. And then that's going to be equal to, well, you got a gamma squared, and now, oh shoot, we got 2 things to mess around with. You got your C and your V and your C square, because we're doing that first term, and then you've got, oh my gosh, what else? We're going to do another bit of addition. I'll do the gamma square and the C and the V and the U, and then let's do where we go, this one and then the first one. Okay, so that's minus gamma squared C U C. Okay, you see that one right there? And then I'm going to do another one that's also minus. It's going to be gamma square times c times u times u. Oh, okay, me? Yeah, whatever. And then we're going to have to do this term over here, which also has 4 terms. Gamma square times v prime times v times c is the first term. And if I'm going to keep that same pattern, I'm going to add onto it gamma square times v prime times, wait for it, v times u, because we already did the one with the c right there. And then I'm going to have to subtract 2 terms again, gamma squared times v prime times u times, so this was a v here, yeah, you have to be very careful, that is a v. And that was a u, so I'm subtracting the u and then multiplying it by c, and the final term is minus gamma squared v prime times u again. Me? Yes, you. Now, things cancel. What do we do? Pink? Excuse me, let's go pink. Some things are supposed to cancel, like this term and this term, they are the same darn thing. Oh my goodness, that is quite a relief. I don't really think anything's canceling on the right side. Do you? I don't. I'm very sad about this. But I want to try to get organized because ultimately we were trying to find out what v is, which is the added velocity of the other two. So I'm going to take all the terms that have v in them and I'm going to put them in a little box and I'm going to factor out the v. And then here are all the remaining terms, and if they go over from the right side I'm going to have to make them negative, and if they're staying from the left side, oh, and by the way, I'm going to put everything that was over here that doesn't have a v in it over there. So the very first term that we have, let's see, our very first term is going to be v prime times c. That's that one, see? Now, this one is going to have to go over on the right side, and it's going to have to be negative, because it doesn't have a v, so we don't like it. It goes over there, and it is minus v prime times c squared. Now, we're going to have some other terms that do have v's in them, and they're going to be moving over from the other side, so they're going to have to change sign. I've got this minus gamma squared times c squared, and then there's a v, but we don't write it because we got that other one right there. Here we got another one with v in it. It's going to be, again, subtraction, because it's moved to the opposite side. We've got gamma squared times c times u. Oh, that's interesting. And then over here, we got another term, but it doesn't have v, so I'm going to write it on the right side because I don't want it over there messing up my left side. Gamma squared times c squared times u. Me? Yes, u. Now this minus, again, no v in it, so I keep a gamma squared. I'm going to have a c. Oh yeah, there's a c, and then there's a u squared. Looks like an A, but it's actually a C. Oh gosh, let's not make a mistake right now. This one has a V in it, so we have to move it to the other side. It's going to have a minus sign. Minus. Minus what? Well, minus gamma squared times v prime times c. And this term also has a v in it, so it's going to be minus gamma squared times v prime. I don't know, the pink's failing us, I think. Minus, okay, this term doesn't have a v, this one right here, so it goes over on the right side. We're going to have minus gamma, oh, it's still negative, right? So there's minus gamma v prime, and you got your u, and you got your c as well. Wow, is algebra fun. This one also stays over here, this last term, minus gamma squared times v prime times u squared. Okay, let's go to the next line. Obviously, I want the left side to say v, so I'm going to divide by this entire quantity. You're not going to like that. I guarantee you're not going to like that. So I'm going to factor some things out in the process. So I'm going to move this up a little bit and move this down a little bit so that we can begin the next line. You're not going to like this one bit. But for all the rest of the derivation, we're going to have v on the left-hand side of the equation. So it really is actually kind of progressy, kind of, sort of, a little bit. I'm going to be looking at the numerator right here, and the numerator has a bunch of stuff with gamma squared in it, and one term that doesn't have gamma squared in it. This makes me happy, so I'm going to take the one term that doesn't have gamma squared in it and bring it out to the front. It is minus v prime c squared, and then everything else has minus gamma squared in it. Oh my gosh, look, everything else also has a u in it. So let's get gamma squared and u factored out of that entire mess. It looks to me like we're going to have, let's see, I'm looking for gamma squared and u. Oh yeah, you. Me? Yes. This is c squared is the only remaining thing when I factor out the gamma squared and the u and the minus sign. You got your gamma squared and your u, and then I'm going to have a plus c times u. You see how that works right there? I'm just dividing by that stuff that I factored out of there, and then this is a gamma squared and a u and a minus sign as well, so it's going to be plus v prime times c. Go figure. Look at all this symmetry here, and then I'm going to be subtracting, oh no, adding because there's a minus sign that's factored out right here. Gamma squared u times, let's see, we're going to have a v prime and a u. Me? Yes, you. Now, close those parentheses. Over here, there's a denominator. I don't know if it makes any sense to change colors of the denominator, so let's just keep with it. This denominator also has this funny structure where only one of the terms doesn't have gamma squared in it, so I'm going to continue factoring out the gamma squared, and I'm going to put that mess in a parentheses. Minus gamma squared even. But the term that's not there is v prime times c. Isn't that funny? Go figure. There's a lot in common. It's positive though, that's negative. Okay, whatever. Okay. Factoring out a negative gamma squared, we get c squared, and then we get a plus c times u, and then we get a, oh man, this one is plus v prime times c, and then this one is a plus v prime times u. Wow, neat. Oh. Now, I'm going to multiply this by 1, which is always my prerogative when I am doing anything in math ever, and I'm going to write 1 as 1 over gamma squared over 1 over gamma squared, because I don't like those gammas just sitting around over there. I just don't like them. Now, 1 over gamma squared is actually 1 minus u squared over c squared. Let me note that right here. 1 over gamma squared equals, well, let's see, it's got to be 1 over the 1 over, oh my gosh. It is simply 1 minus u squared over c squared. So that's really cool. You can check that if you want to. I'll leave that as an exercise for the viewer. Next up. We're multiplying by that, and so I'm going to get that spread onto this v prime c square business right here. But everything else is going to become quite a bit more lovely as we move on with the red. I'm going to get minus v prime times c squared times this quantity, which is 1 over gamma squared, of 1 minus u squared over c squared. Close parentheses, and then I get all of this other stuff, but wonderfully, there's just a u multiplied by the stuff that's in there. So I get u c squared, yeah, me, and then this plus c u squared, see me squared, plus v prime c u, I do, plus v prime u u. I mean, me. Then, divide by, that's this whole stuff, right? Because I distributed that again, well, whatever. You don't always make steps in the right direction, I guess. And then this, oh, shoot. We're multiplying by 1 over gamma squared, and there's no gamma squared in this term right here. So this is going to be v prime times c times the quantity 1 minus u squared over c squared. So that's a little bit annoying, but golly, the advantage afforded by getting rid of all the rest of that stuff, I think is well worth it. Over here, we're only going to have what's left in the middle here. So I'm I'm distributing a minus sign too. So I need to make sure that all these terms come out negative. I'm going to net negative c squared minus c times u minus v prime times c minus v prime times u. Ooh, we're getting really close. Can you smell it? No. Not really. I'm just going to multiply the numerator and the denominator by c. That is 1 when I write it like that, and I'm going to change colors again. What's a color we haven't used in a while? How about brown? Now, when I multiply everything by c, well, some really cool stuff happens. I'm going to multiply everything by c right here, and I'm going to get, well, you see there's a c squared right here that's kind of, oh, actually, that's really neat. And then when I multiply everything by c, oh, wow. Yeah, this is going to be really cool. So I get minus v prime times c squared, and then this is the c squared canceling that that c squared down there. So this is plus v prime times u squared. But then remember I said I wanted to multiply by c, so here I am multiplying by c also. That goes to c to the third, and this gets a c. Now I'm finished with all that funk right there. I'm going to get u minus u times c to the third plus c squared u squared plus v prime c square u plus v prime u prime c. Oh my goodness, I hope I haven't made a mistake. And then I have to multiply the denominator by c. Also, I'm going to get, oh, that's why we did this. Yes, absolutely. So I get v prime times c squared, because I'm multiplying by c, right? And then this has to be multiplied over there, but you've got the c and that's going to cancel out. This is minus v prime times u squared. So I don't have any denominators. I always hate denominators. I get minus c to the third right here, minus c squared times u, minus v prime times c, minus v prime times u. Okay, I forgot something, because all of these are supposed to have the third power of velocity. I've got 3 velocities here, 3 velocities here, 3 velocities here, 3 velocities here, 2 velocities here. It looks like I forgot to multiply by c, and over here I also forgot to multiply by c. Okay. Everything's going to be fine. The next thing to do is to notice that there is some happy cancellation, so we can do that in teal. What cancels exactly? You got a term with v prime, u prime, c. Oh, look at that. He forgot to square this c. See this term right here? It's supposed to, wait a second. No, that's not supposed to have a c. It's just, it is supposed to have a c, but just a single c. This is supposed to be, does that say u prime? That's supposed to be u squared. There we go. All right. Now, I got my teal, and I'm ready to cancel things out. I think that I've got a term here that is, oh shoot, this is supposed to be, this is negative, and this one ends up being positive, but this one was supposed to be negative. Remember this minus sign up here that I forgot to distribute? Let's go back and check it. Oh boy, you're gonna hate me now. Here we go. I got this minus sign here, that was negative. This one is also supposed to be negative, and this one is also supposed to be negative, and this one is also supposed to be negative. So we forgot to distribute those minus signs. I'm gonna have to do that in brown on this line. This is supposed to be negative, this is supposed to be negative, this is supposed to be negative. There. Now, if you catch mistakes, then you know you're doing it right, right? This cancels. With that, what about the denominator? Do you see any v primes times c squared? I do. That one cancels that one. Oh, that's really nice! But you have no idea what I've been doing because it's almost entirely off the page. There, now you can see it. Let's go to the next line. And that one requires me shifting this down. You just kind of have to remind me that I do that so that I don't go back up to that again. I can't hear you. This is equal to, oh my gosh. What should we do? Let's try to get a little bit organized here. Oh man, this is really cool. I'm actually going to just write it all out here as we clean this up. It's minus v prime times c to the third plus, minus u times c to the third minus c square u square minus v prime c square u, and then that's, oh man, just 4 terms in the numerator, ain't no thing. V prime, so that's multiplied by u square minus c to the third minus c square u minus v prime u c. No problem at all, you see? Yes, I see. I think we should go to blue. At this point, I'm going to divide both sides by c squared. What I mean is the numerator and the denominator. And that's kind of a funny move, but I'll show you what I'm up against here. I've got a strategy, and you'll see in just a moment. If I divide by c squared, the numerator becomes really nice and well behaved. Actually, you know what's even better? Let's multiply by negative 1 over c squared. So all of these terms are negative in everything, and we'll just have plus signs when we're finished, which will be really pleasant. But I'm also going to cancel out the c's to some extent. So I get v prime times c plus u times c plus u squared plus v prime u. Oh, what a nice numerator. How wonderful. But the dividing by c squared is going to end up being a little bit of a trouble down here because there are 2 terms that don't have c squared in them. So I'm going to write it like this. I get c plus u. You see that? I got c plus u by dealing with these terms here. But then I have 2 remaining terms that don't have c squared in them, so I'm actually going to write them over c squared because I'm thinking about the form of the answer that I'm trying to get. This is a little bit of a sneaky game. I'm going to write v prime times u times c, and then I'm going to write, it's going to be plus v prime times u squared. Oh my goodness. Now this looks really, really lame, but it's actually amazing when we do a slight factorization, and that factorization is going to come out in the color black, and look how confident I'm feeling we can go into just another one in the same line. I see a bunch of U's and C's. You see V prime right here? V prime is multiplying a C and it's multiplying a U. And also U is you are multiplying a C and you are multiplying a U. Oh, that's funky. And well, obviously C plus U is multiplying a C and a U. And then over here, I've actually got, look at this is really funny. It's V prime times, oh my gosh, what is that multiplying? V prime times U over C squared, which is multiplying C plus U. And the approach then is to say, well, you got your C plus U's all over the place. Let us divide by C plus U. I'm just going to, let's just cancel all of them out. They exist in every term. And we're done. Watch this. We are actually done. V prime plus U divided by 1 plus V prime U over C squared. Sucker! I was just talking to Elise Buckley, who is one of the rare kind of students who's both interested and really talented, and she's the reason that this whole thing happened, because when she reads a book and she finds that it just says, well, you can do this very easily, she actually gets really angry, and so then she tries to do it herself. So one day she came in with all of this algebra written out, and I asked her if I could make a video of it, and there it is. Spaceship is flying away from this monster spaceship at half the speed of light, right? And so you could ask yourself, I'm not going to be really careful with these labels because I just want to set up the problem here. You could ask yourself, if the monster looks at the bullet, how fast does the monster think the bullet is going? And of course, it's unreasonable to say C. The bullet cannot go C. And so we have to use this complicated method of combining the two velocities. This has a, I'll call it like a regulatory denominator that makes sure that the sum of these two does not add up to C ever at any time. So we're going to try to understand how this is possible, because this is moving relative to this, and this is moving relative to this, and so this is moving relative to this, and all the speeds are relativistic, and so it's complicated. It's complicated. That is our relationship with, with relativity. Okay, so what you need first is a diabolical timing device. First you have a source. Oh, that's gross. Let's make a proper source. I'm going to write the word source, and then I'll box it in. There's a source, and the source is sending particles this direction, and they're going at a speed v prime as seen by someone who is at rest relative to the source. Now, the source is not moving according to this observer. I'm going to call the observer O prime, at rest relative to clock. This is my timing device. It's actually a clock. Over here, I have a flash, and the flash is triggered. The next level in relativistic calculations is really adding velocities. You've got your Lorentz transformations now, and you're feeling okay with them. You know, length contracts and time dilates. But who's to say what happens if you have a really complicated situation where like 3 things are moving? This is where it gets kind of gross. I just want to remind you that this is the answer that we're going to be trying to explain today. That is how one thing sees these other 2 things moving relativistically. And here's like the picture. Okay, so this guy right here, this is a bullet that was fired by this little spaceship right here. And the guys in this spaceship see the bullet going at half of the speed of light. But at the same time, this space of the clock, immediately when the detector detects the photon getting there, the source sends out another particle that goes over to the flash, etc. And it's going tick, 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 tick regularly. Now, this L0 is the proper length between the source and the flash, and it's the proper length between the detector and the flash. This is all assumed to be horizontal, and it's the proper length because that's the longest length that anyone will see. So I'm going to call this time delta t naught, which is the time between ticks measured by O prime. This is the time measured by this observer, by observer O prime, and there will be light shot out from this flash when the particle arrives, and it's an automatic kind of thing. It's just chunk chunk, and it takes no time at all. So when this particle gets over to here, and these are probably some distance, what do you want to call it, L naught? Yeah. There's some distance L naught apart, and when they are that distance L naught apart, this is triggered right here, and a photon comes out of here. I'll draw it as a little squiggly a wave packet going that direction. And guess how fast it's going? It's going the speed of light, of course. Everybody agrees on that. And over here, there's a detector. Okay, so you've got your source sending out particles that slam in over here and immediately trigger this flash. And the flash sends a pulse of light this direction, and that's considered one tick